You have to remember to look at that picture because periodically it just goes to blur. Just everything. Okay, so I want to finish up the time-dependent perturbation theory, getting the second order result, and then I want to put in then the dipole interaction. And then that'll lead to basically the first thing I think we'll do is we'll look at Raman scale. So I lied about looking at aspirational curves because we're going to basically have the Raman, so we can actually pick one. Okay, so remember we got this all here. Okay, we're reusing the cat at this point here. We're reusing maybe we're using this. We have that. Okay, so that this H here is this H naught plus an interaction term like this. And then what did we do here? We put this in here. We beat on this, and we ended up with something that looked like. We did that, and then we did something else. We put a lambda in here. That actually we didn't do that. We kept like this, and then we said that the psi. What did we write psi as? Close, very close. And a sum on n, or was it k? I think it was n. Of Cn, which is a function of t. Yeah, this psi and something 0 here. And this is only a function of position. Tell me what this represents here. This is the energy eigenfunction of the unperturbed state. Excellent. That's right. Excellent. Okay. Then times this e to the minus I en0 t over h. Sure. We took this, put it in there. We beat on this thing quite a bit. And I think we ended up with something like this. We're gonna have to check this. Remember, this hi here actually depends on t here. You reach on it's not. Psi 0 r e to the minus I e naught h bar equals I or sum n c dot is that what we had? I was doing some stuff in my head. I think that's correct. I think this IH is just going from this. I think that's in like the next step. Oh. Yeah. And then what did we want to do? We wanted to solve for the kth term. How did we solve for the kth term? How did we solve for CK dot? Their standard trick if I want to solve the kth term here. Multiply both sides by psi k naught star and integrated. And when we do that, what are we using? This is what happens when you don't have homework in the test. Orthogonality. Hence, when you leave, you have. Look at this cartoon here. So to solve for this, we're going to multiply by ck naught star and integrate. Okay. And if you do that, what do you end up with? You end up with summit Cn of t. I'm going to suppress that t dependence. This psi k is star h I at n0 here. This is space here. E to the minus I e n t h bar, and then on this side here we get the psi h bar ck dot. And then this guy then gives us e to the minus e k t. I would agree with that. And then I divided through by 1 over I h bar, and this from here, that gives us this. And then I rewrote this here because I got tired of writing this. I wrote this as a CK0 HI by 0. So that gave us summon e to the I e k naught and not e h bar with a C and I would agree with that. Then what was our next step? We did something with the C's here. We did something with the H here. What was our trick? We express them in terms of lambda. So we said that this HI here goes as this lambda HI. And again, this is going to be a measure basically how important this fellow is here. Because we're going to keep track of the orders here. But then we're going to say that then the Cn, I know the Cn0 plus lambda Cn1 plus lambda squared Cn2 plus dot dot dot. And then we equated powers. When we did that, we had the power. We ended up with this Cn dot 0 equaling 0. And so that means that the Cn here 0. Now, what did we say those Cn0 to represent? They were the unperturbed. And we said, how are we going to assume this? We know that in the unperturbed, if we don't have a time dependent case, if we don't have a time dependent perturbation, the system is going to stay in whatever initial state you're in. The energy is going to shift something, it's going to stay in that same state. And so what we did is that we said that what this is going to be, that the CN0 here is going to really be delta and I. So we're going to say that the state is initially the initial state. That makes sense? And so what that gave us is this. Okay. We said when we solved for the C1 case, the CK1 term, we ended up with this. We ended up with sum on n, Cn0. This guy. H bar. That's what we had for the first order term. Then we took this and put it into here, and that gave us this. All the n terms are going to be 0 with the exception of when I equals 1. I mean, when n equals I. So this gives us then what did we take this k to be? We took this to be in the final state. Like that. And so when we solve for that gave us this. This gave us C final 1. Well, I'll leave it as k. Here, 1 over I h bar integral. I can say from minus infinity to t. Where equals ck with t. Next one. Okay, where's my mistake in here deliberately made?
You need T prime.
Correct. Because this actually is a fixed t.
Also,
Okay.
shouldn't she be going off of F's instead of K's?
Okay, I should be putting an F there, but I'm going to leave it as K just for a second. But yeah,
Okay.
that's I backtracked from what I said, but yes. So we have to put a prime here like that because that's actually what we're calling a dummy. And we said that we can actually pull this piece. Well, we can't pull that piece. And we did one more thing with this HI. What did we do with the HI? We assumed a time dependence. How did we assume a time dependence on that? So that these HIs here are very frequently going to be some HI, I'll call it prime, which depends just on position times the e to the plus or minus I omega t. So this HI here really depends on t. It's a function of t. I'll put a prime there. So I can rewrite this as the following. Does that make sense? And then what did we get from that? We ended up getting Fermi school. So we use this. To drive. Fermi. Everyone happy with that? Good.
We're thinking about posters and we just got the text that everyone will be presenting both days. Yeah.
Okay. Okay, actually could dress up like pirates. They have like swords. Throw Colin's office. Sort of. Have little glass parrots on the phone. Yeah. Little glass peg legs.
Black eye cactus.
Pretty cool. Yes. Okay, questions there? Okay, now I want to get to the second order result. So the second order result is this. So the second order one is to work these out. And we did. That's what the second order result becomes. And basically what happens is that this is the first order result. And this is the function of t. This. Okay. Now to make this as general as possible, I'm not going to put in this form here. Not yet. I'm going to put in this form here. I'm going to take this form here. And put that in here. Okay. And then I want to solve this too. So what am I going to do? I'm going to say that this guy here, this is CK dot, the second order is really dck2 dt. What I'm going to do is take over the dt and then solve this thing for CK. This gives me CK2 equals sum on an integral. And then this whole thing. Okay, what I'm going to do next is not hard. The only thing about this is be really, really careful with indices and really, really careful with the variables. I could say, well, that's true on everything. Yes, that's not the point. Right now, I haven't done that substitution yet. I haven't done the substitution on anything like this. Now, this is going to go from some minus infinity sometime in the past to the present. Now, tell me what I have to change in here. What do I have to modify in here? Where the Scooby-Doo ring, Raggy. The same thing. If this is a T here and if I'm in a good anti, these have to be primes. That makes sense? You say, well, fine, you know that. The next part becomes more subtle. Now let's do the substitution here. So now I'm going to take this, and now I'm going to substitute that. Tell me what I have to be really careful about now. So first of all, this K goes to what? This K here goes to, but this is true for any value of K. I'm putting it in there. This K, and this K, they have to go to N. So I have to change the K to N. Now, this T here becomes what then? According to that? This T now becomes T prime. So this becomes T prime. What has to happen then to this T, and this T? It has to become T double prime. Okay? So, question is, how do we fit this on the board? I think that's sort of like, everybody remember those small. I'm going to have second order coefficient. It's going to equal, oh, damn it. There's a 1 over IH point here as well. I dropped that. So you can get a 1 over IH. Here that dropped. Sum integral from minus infinity to T. I'll have a big bracket here. Big bracket. I'm going to put this in here. So this will become 1 over I. Integral from minus infinity to infinity, T prime, e to the I, e n 0 minus e I 0, T double prime, H psi n 0, H I, T double. That's my CN1. Now I have this term. T prime. That's what I have. That makes sense? Now, what will I write for this fall here? And what will I write for this fall here? We're going to take the special case where I can write those as some function of position times a harmonic term. So I'm going to write this from here as some function of position. I'll call this H I of R of double prime. I'll just match with this double prime here. Or maybe we should just call it. E to the plus or minus I omega T double prime. And this one over here, I'll call this HI, this is R prime. That just matches this prime here. Plus or minus I omega T prime.
We wanted to-
The second, oh, this one should be divided. Sorry about that. Yeah. This is why people set H squared to 1. This one has to be this. There's a reason why. Okay, so now, look. Okay, so let's actually kind of work on this. So what do we have? We have 1 over I H bar upon C squared. I'm going to have an integral from minus infinity to t to minus infinity to t prime, a sum on n here. I'm going to have, I'll put this term first. Psi k0 h I r prime psi n0. Now put this piece with this piece. I'll put in this piece. For all those exponentials. This. Yeah, I think I have all the terms, right? Okay. Now, what can I do? I can actually now do the, and then I need one other thing here. I need dt prime, dt level. That have two of those. Okay. So I can actually do, let's look at the t double prime integral here. If you look at the t double prime integral, I have this guy. That one goes from here. Okay, what does that equal here? That's going to be basically 1 over I I en0 plus or minus h bar omega minus e naught I 0 here times this e to the I en0 plus or minus h bar omega minus ei0. I'm going to put in the upper part here t prime all over h. That makes sense? Now, with this lower limit part here, what did we say about the lower? What did we say about the interaction term coming in? It's not going to really count. And so you could say, well, what about evaluating this lower part here? I'm not going to worry about evaluating it. I'm going to say, well, it doesn't. It weighs out of this. Does that make sense? Okay. Now, if I just then kind of draw this guy here. You know, this is why when you become billionaires, you have to donate enough money to Alfred, get a really big blackboard with, you know, this recording system. But as soon as it walks in, it knows it's me. It gets everything popped up. And then it just have all the whiteboards along there. And it'll be my group. When you end up getting like $1 billion.
Don't know why, but it's.
I'm gonna end up with this 1 over IH bar. I've done now this integral here. I'll have this minus infinity to infinity. The sum of sine A0 H R double psi 0. Now this piece and this piece coming. I want to do a little picture. Now we can see the Feynman algorithms coming in a little bit better. What I can do is I can represent this picture like this. This point here is going to be R double prime, T double prime. This point here is going to be R prime, T double, T prime. Okay. And this right here, this is going to be my H bar omega, and this is my EI0. This is I'm going to write this. I'm going to give you time. This is giving me my E final. This and this is and this right here. This is my E. Okay. Actually, I guess it's going to be called the same. This is K. This K here is going to go for the final. So again, Feynman's genius is to realize that basically every part of that picture, every part of this picture corresponds to this. So what Feynman realized is that this piece right here is actually this vertex right there. So this is your initial state. Here's your initial state. Here's your interaction. This interaction is that Hamiltonian, whatever the interaction is, and you have that state coming in here. And then what happens? Well, this interaction causes this initial state to go to some state here at n. So this is a sum on n here. And how many n's are there here? A whole bunch of them because they're summing up. This right here, these are called virtual states. And what do they correspond to? They basically are going to correspond to basically your system is going to start at some initial state. It's going to be picked up from this interaction here, some virtual state. And then that virtual state is then going to fall down some. That's what's going on. So you have an initial state here. The interaction results in that initial state going to some virtual state. This right here, this whole piece here, this is your prop. What's called a propagator. Okay. This is kind of the propagation part there. So this part corresponds to that here. This part here corresponds to this little guy here. And this part here corresponds to this little part here. And what are you doing here? And I do that sum goes into all that stuff as well. And so what are you doing? You're integrating over all possible time values here, over all possible t prime. We've already integrated over all possible t double prime. So when you do the actual calculation, this point and this point here can occur at any time. Doesn't really matter. Okay? Does that make sense? When you see a diagram like this, again, Feynman's genius was to realize that this picture here actually corresponds to the picture. So he could write down the picture, and then from the picture, he could ameliorate it. And so you saw all the work we had to do to get this expression. Feynman, you don't have to do that. Feynman, you basically draw the picture, and then you get it. Okay? And this propagator here, I should have the sum on n here. The sum on n actually goes to that. It actually becomes something called a Green's function. Okay. But when you look at basically Raman scattering, what do people say about Raman scattering? You're in some initial state. What happens? You get scattered to a virtual state. And then you can come down to another. You can come down to a different state. Now, what can happen here? When you look at these, okay, are there any questions?
The same derivation that you did.
Is part of
I
it.
don't understand how you write at H bar and E.
Oh, there should be another. Oh, there's two of the pieces in there. I dropped one of them. So there's this guy, and then there's this corresponding guy here as well. I dropped my guy there. So there should be, in fact, there should be the E to the I, E, and 0. Plus or minus h bar omega minus e I0 t prime. I dropped this piece here. So yeah, both pieces go.
The H bar and E are multiplied, or it's in the power.
Oh, which part here? This down here?
Yeah.
That is not in the power. That's in the denominator.
That's the denominator.
Yeah,
What
so
about H bar?
This h bar here is in the numerator. It's taken off. Does that make sense? Now, what could just as well have happened here. You can also, when you go through and work it out, you could also have this picture here happen. This is another one of these processes that can happen, where the particle actually emits the photon first, goes to an excited state, and then later on it's actually absorbed. This term here is called the direct term. This piece here is called the exchange. Now notice what happens here is that these virtual states here do not conserve energy here. Okay? You can get away from it because of the Heisenberg uncertainty principle. The Heisenberg uncertainty principle states this.
Your primes are wrong because your first one should have a double prime and then one of them should have a single prime.
No.
No?
That one, this one here has a double prime. I did the integral here. So here I did the double prime.
Never mind.
And then but I could easily make the okay. State. Oh, yeah. Then I put in the upper limit here like this.
Okay.
And I said the lower limit, and let's just throw it away. You have to do something fancy.
So then if those E's are the same, then wouldn't it make more sense to combine them together?
You can, but there's a subtlety. But that's exactly
okay.
Okay, so what you're going to see happens is that when you combine them together, there's string cancel the string here. Okay. Like that. And then you have to be a little more careful with the H bars. So there's a reason. There's some sleight of hand. Okay. Because it has to do with how these this looks like a plus or minus, this looks like a plus or minus. However, when you work it out, it's actually a little, you get a plus one. So there's some, I'm doing a little change. Okay. That makes sense. Okay, so what happens here is that these virtual states here, they do not conserve energy, which is what why they're virtual. So when you look at the Heisenberg uncertainty principle, one of the versions of it is this. That states that you can violate energy. This is your violation of energy for this period of time here. What happens here is that this virtual state here does not conserve it. Because you could say, well, wait, isn't this energy plus this energy here equal to this energy here? And so that bottom would then go to 0. Yes, unless energy is not conserved. Energy is not conserved. Okay. So what happens in Raman scattering, the quantum theory is this. But if I have some states here, these are very virtual. I can actually go to this state here, I can go up to the state here, and I can fall back to that same state here. So if I get excited to this virtual state and come back to the same state here, this is called a Rayleigh scalar. And that's your dominant type of scalar. Well, what else could happen here? I could just assume, I could go here. I could get scattered up here, and then I could actually go down to a state like that. Okay. And that one's either Stokes or anti-Stokes, and I can never keep track of which is which. This is either the Stokes or the anti-Stokes. Well, what else could I have? I could go here. It's scattered to here. And then fall to a lower state. And this is going to be the opposite one. So this is either Stokes or Stokes. So this one is Stokes, this one's anti-Stokes, and this one is anti-Stokes, and this one is Stokes. I can never keep. I learned them, and I'm convinced now I have basically a squirrel memory for this. I learned it for like a minute, and then if you're asking me a minute later which one's which, I have a squirrel memory for which one is which. I just remember one is Stokes and one is anti-Stokes. Now, which one would be larger? So in other words, if you look at actually the likelihood being given off here. I'm going to plot the intensity here. Like, I have this big peak here. This is going to be for Rayleigh scalar. And then I'm going to have one being this, another being like this. So again, one is Stokes and one is anti-Stokes. Okay, which is which and why? So I'll call this A. I'll call this one. This is which one here is A and which is this A or B or is this A? And why?
Low wave. Release more energy, so it happens in the higher wave longer.
Well, I'm just trying to think about like the height of these guys here. So which one would be, because one will be, if this is omega naught, so this is some omega naught, then this would be omega naught plus some delta omega, and this would be omega naught minus. Which one is which? I might have to change that. So which one will have lower energy? A or B? B is going to have lower energy here. Does that make sense? So if you look here, this is actually less than this one here. This energy here, so it's gonna have lower energy. This one here will have higher energy, so this is the debate. But why is this one higher? And this, yeah, why is this one then? I think I have this picture. I think I have to have. I have to have this one up here higher. Why is this one here going to be lower? Right.
Lower energy.
Now, what do you know about the probability of being filled in these states as you go from there? Remember, you have the C to the minus E, well, this beta. Right? As your energy increases, the probability of being in a state is lower. So what's going to happen here? If this state starts here in an upper state, you're less likely to be there. If you start over here, you're in a lower state, you're more likely to be there. So what does that mean? You're less likely to be here. You're not designing occurs frequently, and as a result, this connection is in the lower. Or we should say lower. Does that make sense?
Did you write that on the board?
Yes. Question where? So when you go to your qualifying exam, that's probably going to be a common thing, because I know you're just asking us. Okay, first of all, figure out which one's so. So don't go over without knowing which is which. Okay, just don't do that. Don't. I could do it because I'm not going to be a qualifying exam. But don't go and know which is which. But they're going to want to know about the difference here. In other words, why is this one lower in energy and this one higher? And they're going to want to know why. So this one, what happens here in this case? The probability of occupation is given by, this E to the minus beta E over Z. It's a Boltzmann distribution. Okay, in A, the upper level state. I'll say the initial state. Is higher in energy. And less occupied. As a lower probability of occupation. So the intensity is lower. What's over here? And B, the initial state is lower. And more likely. Hence. Like, that makes sense?
Yes.
Now that's the quantum theory for this. The classical theory is a little bit different. I think I'll go do the classical theory on the and then the Riemann scattering is, well, it's not. that was kind of the big broad part of the theory. Does that make sense? Is that helpful? Okay, we're done. Enjoy making posters.
Happy readings.